Hi everyone, welcome to today's tutorial. So this is a physics question from tutorial sheet 1, and if you have not yet subscribed to the channel, make sure that you do so immediately or just before watching the video. And if you have any mathematics or physics question, feel free to ask using these contacts on the screen. Alright, so let's quickly do the question. So the question is, a spring that obeys Hooke's law has a spring constant K. Show that the energy stored in the spring when it has been extended elastically by an amount X is given by that. So this is something that is very straightforward. So if you want to derive this formula, the first thing that should come in your mind should be the acceleration of an object that is undergoing harmonic motion. So you are going to have this acceleration, which is just equal to negative omega squared a cos omega t. So don't mind these lines going up. Okay, so what you have is simply just the acceleration there, and then at the initial conditions when t is equal to 0, this part becomes a 1 because cos 0 will become a 1. So you are going to have a is equal to negative omega squared a. So remember what we said, or rather in the question they are saying it has moved the amount X. So when you have a spring and then it moves from its equilibrium point going this side, the maximum distance it's going to cover from the equilibrium point is called the amplitude. And now in this case they are saying it has moved the amount of X. So this X is the one that we're going to replace on the amplitude. And you also remember, so in short we're saying the amplitude is equal to X. And you should also remember that acceleration can also be written as dv dt, which can also be written as dt d2t d2x t2. So we are going to write the dv dt there, and then this is just going to be equal to, and then omega there, if you remember very well, omega, we said omega is equal to k over m, the square root of k over m. And then if we say omega squared, it means that we're squaring this side, we also square this side. So on the other side, this side will just remain with k over m. So while there is omega there, we'll put k over m. Then while there is a, we're going to put x. So from there, what we are going to do is we cross multiply. We can cross multiply, or before we do the cross multiplication, let us first multiply dv dt with dx. So dx times dv dt. So when you multiply this dx is just the same as multiplying nothing to dv dt, because dx over dx is simply just 1. 1 times dv dt will give you the same dv dt. So this other side we have negative k over m x. So we can switch these, we can exchange them. So we're going to have dv dx times dx dt, and then this is just going to be equal to k over m x, negative of course, but remember that dx dt, the change in displacement with time is simply just velocity. So at dx dt there we can just put velocity. So we have dv dx, and then v there is equal to negative k over m x. So we're going to multiply the whole equation with m. We multiply the whole equation by m. So when we do that, we're just going to have mv dv dx, this side is equal to negative kx in short, not over anything. So from there we can cross multiply now. So dx will come that side. So this side we have mv dv this other side will have negative kx dx. So when you do the integration on both sides, this side the upper limit will be v, since we are differentiating this with we are integrating this with respect to v, and then the initial or the lower limit will be 0. Here the lower limit will be 0, the upper limit will be x, because we are integrating with respect to x there. So from there we can do the integration. So after integrating this with respect to v, you just get 1 over 2 mv squared, then plus c1 is equal to this side, when you integrate with respect to x, we have negative k over 2x squared plus c2. So let us just take everything to one side, and then the constants we put them on the other side of the equal sign. So when you do that, we're simply just going to have half mv squared plus half kx squared is equal to c1 minus c2. So this c1 minus c2, we're just going to take this as energy. So we say let c1 minus c2 be equal to the energy stored in the spring. So we are going to have energy is equal to half mv squared plus half kx squared. So now, having derived this, remember that at one point we learned that okay, let me just start on the new page. So at one point we learned that the displacement of an object undergoing harmonic motion is given in terms of time as a cos omega t, and then the velocity is found by differentiating that, which is just going to give you a negative a omega sine omega t. So after doing that, after writing that, we can replace this in the formula. So we had the formula, which was just E is equal to this one here. E is equal to half mv squared plus half kx squared. So we have E is equal to half mv squared plus half kx squared. So what is what is a x rather, we're going to put that, and then what is v, we're going to put that. So we say E is equal to half what is v, I'm going to put negative a omega sine omega t. This omega is simply just the angular velocity, and then say plus half k. Remember k, I think let us also change k in advance, or before we can even do that, let me just leave it like this. I'll change it at the end. So half k, where there's x, I'm putting a cos omega t, and then we square this. So E is equal to half m. When you simplify that, this will just give us a squared omega squared sine omega t. Then here we have a plus half. This will give us k a squared. This will give us kx squared, and then we have ka squared, and then we have cos omega. Rather, this part is supposed to be squared as well. Even the cos is supposed to be squared there. Yeah, so we can also change this part k. Remember, we knew to say, or we learned here from this expression to say omega squared is equal to k over m. So k over m, we said, is equal to omega squared. So the value of a becomes m omega squared. So what is k, we put m omega squared there. So we can put m omega squared here. Now we can factorize the common things. So we have half, then we have m is common, we have m there, we have m there. Oh sorry, I made a mistake, I erased a instead of k. Okay, so I'm supposed to erase k, not a. So this a is also supposed to be squared there, since there's a squared outside. Alright, so from there what we do is we say half m is common, m is common, we have a is common, a squared is common, then we also have omega squared, which is also common, and then in brackets we're just going to have sine squared omega t plus cos squared omega t. So there the value of e will simply just be equal to half m a squared omega squared. But when you look at this part, this is a Pythagorean identity, which is just equivalent to 1. So when you simplify this, this will just be half, and then remember omega squared is simply just equal to k over m. So we're going to put k over m while there is omega squared. So we are going to have half m a squared, then while there is omega squared we put k over m. So this m and that m will cancel, so meaning we just remain with E is equal to, which is the energy stored, is equal to half k times a squared. But when you read the question says it moves an amount of x, and we said the value of a is simply just going to be taken as x. So meaning on this expression, in this expression rather, while there is a, we're just going to put x. So the value of e now simply just be equal to half k x squared. Hence shown. So we have showed that the energy stored in the spring is given by that formula. That is exactly how you find. Thank you very much for watching today's tutorial. See you in the next tutorial video that we're going to have. My name is Harmtedy. Please don't forget to subscribe to the channel. Shalom, shalom.